Hi everyone, my name is Farid Zidat. I am a PhD Senior Application Engineer within Altair. I am going to present you and show you how to make first spatial magnetization and how to make the skew of this spatial magnetization. Why this topic today? We can, for instance, have a magnet like this, kind of a ring, but having like skewed magnetization. This is something we can do geometrically, right? So we can create regions with different magnet and make in this case a radial magnetization for each one. Okay, so there is no but the issue here is that if we want to make a cooking torque computation, we need to have a good mesh and extrusive mesh, and here is not really the case. We can have like a mapped mesh on the faces and so on, but unfortunately we cannot do it better than this for this kind of geometry. And the cooking torque can be also not a very good one because it is really sensitive to the mesh. So this is really the interest spatial magnetization applies. So you can use spatial magnetization to create Halbach or sinus magnetization. And here we are going to see it how to make spatial magnetization, radial magnetization, and skewed magnetization. Okay, so I'm going to show you the other project where I applied this. So here you can see that this is the same geometry, but in this case, it is a full extrusive mesh, and it is really regular mesh because I can use linked mesh on the different portions. So this is a really very fine mesh and adapted mesh to compute cooking torque. So one can say or ask a question, why to not use flux skew in this case? Yeah, flux skew is a good idea, but in case you have magnet overhang, flux skew cannot deal with this kind of 3D effect, okay? So once again, this is really the interest where we can apply spatial magnetization. So to create a spatial magnetization, I need to create a material, right, with analytical model, which is a spatial linear magnet, right? Then here I can put a vector, and here where I can apply what I want. For instance, you can apply unidirectional or parallel magnetization simply by creating a vector. We can create a vector here, vex3d. So I will put one here and one for y and 0 for z. Okay. So then if you display the magnetization, you can see that it is unidirectional one. Okay. So if I want to make positive and negative, then I have to create parameters function of valid. So I can use the valid function to say that from 0 degree to 90 degree, I will use positive. So I will keep it as it is here, plus another valid from 90 degree to 180 degree with minus orientation, so to make opposite orientation, so I can have another orientation. So the spatial magnetization is very easy. So let's come back to our interest is to create radial positive and radial negative orientation and skewed in the same time. I will delete the arrows here. So what I need for that? So I need first a parameter giving me the total length of the machine, which is 10.5 millimeter. Z0 here is the initial position, so this is the point here. So the coordinate of the initial one. I need to create a parameter alpha, which is the inverse of tangential of y divided by x, right? So this is the angle. For each xy, I can compute the angle. So for each point on the magnet, I can compute its angle, alpha. And then I need to create here another alpha, but also depending on the z coordinate. So because the first alpha I created is only depending on xy, so I need another alpha 2, which is depending on the z direction, because I need to skew, because it's not straightforward. There is an angle here, so I need to find this angle. So the alpha 2 is depending on the first alpha I created, plus beta here. Beta is the parameter I created also, which is the skew angle I need. Here in my case, I need 34.51 degree, which is the angle of my skew. So then multiplied by z, this is coordinate z, plus z0, the initial one, I divided by the z total, okay, minus the rotor position, because the rotor will move. I need to keep this spatial magnetization for each rotor position. As you can see here, I use modulo and 180 degree. So this is in order to respect the periodicity. So when it arrives here, I am sure that I will always have a good orientation and the good alpha. So yes, this is once you created alpha 2, the big part of the work is done here. I need then to create another parameter xbr, ybr. So xbr is depending on alpha, the first alpha I created. YBR, sorry, is depending also on the alpha, first alpha I created. Then I need to create A1. A1 is a vector, right? Multiplied by a function valid of alpha 2. So from 0 to 90 degree, I will have positive radial orientation. And A2 from 90 degree to 180 degree, I will have negative radial orientation. So then I have all parameters I need. I will create now parameter skewbr, which is A1 plus A2. So once again, I will repeat, I need to create those parameters first. Z0, which is the initial coordinate of the starting of the coordinate of the magnet. Z total, which is the total length of the magnet. Beta is the skew angle I need. Then I need to create a parameter alpha, will locate each point on the magnet, depending on xy. And then since it is skewed, so it's 3D1, I need alpha 2 depending also on the z. So here I will use modulo alpha plus beta multiplied by z plus z0 divided by z total minus AO parameter pose, which is the angular position, and 180 degree. So alpha is once again to locate each point on xy plane for the magnet, plus beta, which is the skew angle, multiplied by z, which is the coordinate according to z-axis, plus z0, which is the initial coordinate, divided by z total, minus the parameter AO parameter pose, and this is modulo in order to respect the periodicity. Once I arrived here, I am sure that I will always have this periodicity respected in my spatial magnetization. Okay, so E pose here, just to show you that pose is ank pose rotor, which is the position of the rotor, right? Okay, so once you did that, we will create then the parameter xbr, which is depending on alpha, the first alpha I created, ybr, sin d alpha, and then I will create A1, which is the vector of XBR, YBR, multiplied by the valid on the alpha 2 from 0 to 90 to have positive orientation, and A2, which is depending on XBR, YBR created, multiplied by the valid of alpha 2 from 90 degree to 180 degree. And here I have minus to have this negative orientation of the magnet. Okay, so this is all what you need as a parameter. Then I have to create skew BR, which is A1 plus A2. Then I can go back to my material I created, and I can replace now this vector multiplied by, so I can use it here. Multiplied by 0.54, which is the BR of the magnet. Okay. Right. So then this material you created, you should assign it to the region, volume region, magnet 1, material 1. So once again, the interest here is that you can use extrusive mesh and a linked mesh on the portions, and this means that you will have really very good mesh adapted for cooking torque computation. Then you can go and display the rows. As you can see here, they are all in red. Why? Because I am using rotor position here, which is, if the project is not solved, Flux do not know this initial position. So I will just replace it here by 0 in order to show you the results. So this is the result that you need to have in order to perform this spatial or radial spatial skewed magnetization. Right? I will just go back here and instead of 0 use again my AU parameter I created previously, pause. Okay. So this is for the radial skewed magnetization. What about, let's say, spatial skewed Halbach magnetization? Okay, so for Halbach, we are lucky because we have already the macro called Halbach magnetization 3D. So how to load it? You have to go to macro, right click, load the macro, go to macro 3D physics, and you have this Halbach magnetization macro. One right click on it, run it. So it asks you what is the flux remnant BR you have for the material characteristics, the relative permeability, the angle where you have the BR is max. So if I put, if I make it like this, so then you need to have like, sorry, maybe I will change the color. You need the magnetization to be like this actually, and then sinus like this. So the maximum will be at 45 degrees in my case. The sinus, the maximum of my sinus will be at 45 degrees. So the number of poles, I have 4 poles, so the number of pole pairs is 2. You need to select the magnet and then apply it. So when you apply the macro, it will create parameters BR, NPP, which is the number of pair poles. It will create theta 0, theta P, VEC, XP, and YP. In my case, I need to create beta, which is the total angle of the skew. Once again, Z0, which is the initial value of the coordinate, and Z total, which is the length of the machine. So the theta P here is depending on XP, YP, and so on. So the initial magnetization, if you want, will be Halbach and non-skewed. Here you can see that the macro will create Halbach magnet with this VEC parameter, and the VEC parameter is using theta P, right? So let me display here the magnetization. Okay, so it is not skewed. What I need in my case is to have this Halbach magnetization but skewed. So I need only to create theta PS. Okay, theta PS here is depending as the theta ps initial created by the macro. So theta p, this is what created by the macro, and theta ps s to say that it is for skew. It's exactly the same, but I need to add the skew angle in my case plus beta minus z plus z0 multiplied by beta divided by z total, and it's done. This is all what I need. So I just modified the angle to adapt it to my skew angle here. Okay, so the vec parameter which was using this theta p, I will replace it by theta ps. Okay, physics, display a role. Alright, so here as you can see, I have a spatial Halbach magnetization and skewed one. So really, this is really powerful tool we have here in within Flux in order to have a mesh, a full mesh extrusive and really linked mesh, so a regular mesh. This will allow us to have really a good cooking torque. So if I come back to once again the cooking torque I had with radial skewed magnetization, this is it. As you can see, it's not really symmetrical. But when I use a spatial skewed magnetization, radial skewed magnetization, I have really a symmetric cooking torque, which is what is expected in a rotating electrical machine. Okay, so that's all for me. Once again, the purpose is to show you possibilities offered with spatial magnetization. So we have seen how to create spatial magnetization, and we have seen how to make it skewed spatial magnetization. Please feel free to contact us on the forum or the support if you need more information or more help on it. Thanks very much. Bye.